Okay, great. Thank you, Benedetta. It's great to be here. Today I'm going to be talking about works that I've done with two different groups. And of course, these are projects that I haven't done alone. I have a lot of great collaborators that I've been working on these things with. So to ease us back in from coffee break, let me start with a very general statement, which is that we would like to understand the laws that govern the universe. And a kind of caveat to this is that a lot of astrophysical processes do not proceed under Earth-like conditions. We need to go to kind of astrophysical cases to observe a lot of these physical processes. So luckily for us, and I know I'm preaching to the choir here, galaxies are both tracers for cosmology, and they're also, which is more pertinent to this conference, laboratories for astrophysics. And I try not to say, you should obviously know this, but I hope that everybody in the room knows that we cannot change galaxies, we can't perform experiments on them, and that we need to leverage the existing population of galaxies to measure astrophysical processes. And in this talk, I'm going to be mostly focusing, or really entirely focusing on low-mass dwarf galaxies. So, let me assert that dwarf galaxies are exceptional cosmic test pieces, especially for measuring the star formation cycle. And before I kind of substantiate that, I'm going to step aside for a little bit and define exactly what I mean by dwarf galaxies, because even within the kind of dwarf galaxy community, depending on who you talk to, you can be orders of magnitude different range in stellar and halo mass. So today I'm going to be focusing just on the bright kind of / classical dwarfs. So these we're defining as galaxies with stellar masses between about 10 to the 7 up to a few times 10 to the 9 or 10 to the 10 solar masses. So I said that dwarfs are exceptional cosmic test pieces. This is because they're kind of definitionally selected to have a shallow potential well and low densities, both in their stars and their dark matter, and low metallicities. So because they have a shallow potential well, their galactic structure is differentially more sensitive to the nature of dark matter, to star formation feedback. And you can see that in work, including work that's been done by people in this room, looking at kinematically selected outflows from dwarf galaxies, predictions on how the structure of dwarf galaxies might be sensitive to star formation feedback, and kind of these very visceral kind of test pieces of dwarf starbursts in the local universe. So because they're low density and low metallicity, we can also think of dwarf galaxies as kind of extreme star forming conditions, where I'm defining extreme as very different from the Milky Way. And these are useful for kind of increasing the dynamic range of scaling relations, which we've heard about earlier this morning, looking at the relationship between things like pressure or midplane pressure and star formation feedback, and investigating how interactions between galaxies can affect star formation in these low-mass systems. So this is just to say that dwarfs are kind of ideal laboratories to study the star formation cycle. And what I'm going to be talking about today in particular are two projects, one looking at driving galactic winds in dwarf galaxies, and the second at looking at quantifying the distribution of star formation. So if we start at the beginning, we can ask how efficiently does star formation in dwarfs drive galactic outflows? So why do we care? Well, star formation feedback drives galactic winds. These winds remove gas for future star formation, so self-regulation of star formation. The wind driving efficiency is therefore key to our understanding of star formation regulation. But specifically in this stellar mass regime, or this mass regime in general, theoretical predictions can still vary by a factor of 1,000, depending on whether you're looking at ISM scale simulations or these more cosmological big box simulations. So we'd like to know how efficiently does star formation drive winds in low-mass galaxies. And we can kind of define a metric for this efficiency, which is called the mass loading factor, which has already been mentioned this morning, which is just the ratio between the mass outflow rate and the star formation rate. And we can spatially resolve these outflows only for kind of vigorous and nearby cases. And this is a game that people play. This is a game that people in this room have played, and a lot of effort has gone into measuring mass loading factors for, or direct observations of mass loading factors. But we can also approach this from a slightly different angle and say, well, star formation-driven outflows remove gas and metals from the gas reservoir of the galaxy. Star formation also locks metals into stars, and the stars themselves, of course, enrich the gas. So the efficiency at which star formation drives outflows also governs chemical enrichment. Ergo, chemical evolution can also tell us something about outflows. However, as I think this audience is very well aware, simulating or making realistic galaxies is very hard. So the game that we're going to play is kind of to work backwards to measure the mass loading factor from chemical enrichment. So we say that we have this observed set of galaxies where we know the stellar masses, the star formation rate, the gas phase metallicity, and the gas mass as a function of time. And we're actually going to use our lowest redshift sample as our boundary condition, where we're making this statement kind of tautologically that they must be realistic galaxies because they are a set of real galaxies. Then we can take this heavily simplified model for this very restricted part of stellar mass and redshift space. So this is just for low mass galaxies and just from redshift 0 to 0.2. This is not extensible for more massive galaxies or to higher redshift. And we're essentially saying that star formation makes stars, star formation drives outflows, and star formation produces metals. And I'll just take an aside here and say that our fiducial model assumes equilibrium between inflows and outflows, but we've varied the inflow assumptions and also varied the differential enrichment between outflows and the ambient ISM, and this really doesn't change our final estimate of the mass loading factor. But this model allows us to estimate the change in stellar mass and gas mass and in gas phase metallicity. And crucially, we also need to select a sample where we know very well the observational constraints. So what's the probability that we would put a fiber on a galaxy with the predicted properties, and what's the probability that we would achieve redshift success for that galaxy as we redshift our lowest redshift galaxies up backwards in time. And this allows us to predict how the sample should evolve in redshift space or in look-back time. So to do this, we really need a large sample of low mass and low redshift galaxies, and specifically with a well-understood selection function, because this is based off of the understanding that any redshift evolution we see in a sample is really a combination of both physical evolution of the galaxies, but also the observational evolution of what types of galaxies we will select given our sample at a given redshift. So the way that we've approached this is with the SAGA survey, with the caveat that I'll explain in just a second. So the main SAGA survey is a survey of 101 Milky Way-like hosts, looking for the satellite systems around those hosts. So 378 satellites, that is 94% mass complete down to stellar masses of 10 to the 7.5 solar masses. We recently had our third data release papers, so including the main survey paper, looking at the environmental effects on star formation, and extending the universe machine quenching model down to SAGA satellite masses. And this is really focused on the satellite systems around Milky Ways. So if you're interested in that, I would encourage you to check out either the papers or the associated e-posters. But getting back to the kind of sample at hand, I said that we need a large sample with a well-understood selection function. SAGA certainly has a well-understood selection function, but 378 satellites is not a large sample, and it clearly has an environmental bias because we're selecting for Milky Way-like hosts. So actually, the SAGA main survey is not what I'm going to be talking about today, but rather I'll be covering the SAGA background sample. So the main survey has 378 satellites, but we actually took more than 40,000 spectra. And these background spectra, because of the photometric selection, tend to be low mass and low redshift galaxies. And because they're part of the SAGA survey, they also have a well-characterized selection function. So here I'm showing redshift versus stellar mass. The blue histograms are the SAGA background sample, and the orange curve is kind of the approximate gamma limit. I should also note that the actual satellites themselves are all excluded from this sample. And taking the SAGA background sample, this allows us to really rewind the star formation cycle. So here, each panel is going to be mass metallicity from direct temperature methods at the bottom, and then star forming sequence at top. Blue is always observations, orange is always predictions. And you can see that we can trace the evolution or the observed evolution of the star forming sequence and mass metallicity out from redshift less than 0.03 out to redshift 0.2. And I should again say that in all of these panels, the quote-unquote evolution that you're seeing is really the combination of both the physical and the observational change in the sample. So, having done all that, we can then back out our best fit mass loading factor, and we find a mass loading factor of about unity, 0.92, and this is in good agreement with direct observations. So here I'm showing stellar mass versus the estimate of the mass loading factor. The blue cross here is our work, and the kind of bold points are the median of other direct observation samples. So I would stress here that there's really the emergence of a consensus on the observational side, despite very different assumptions. So our model makes a lot of assumptions about the ISM and how it mixes, whereas direct observations of the mass loading factor make a lot of assumptions about geometry, and when you kind of try to back up the mass outflow rate, you have the issue of either you see where the gas is because it's edge on, but you don't know how fast it's moving, or it's moving towards you, so you know how fast it's moving, but you don't know where the gas is. But despite this, and despite the different assumptions, we're really reaching a mass loading factor of around 1. And I stress that because if you look at the observational side, if you look at the theoretical side or simulation side, it's a very different picture. So now I'm showing our work again in blue, but compared to kind of contemporary simulations. So a mass loading factor of around unity in this stellar mass range is in agreement with ISM scale simulations, which are in green here. But it's much lower than what some contemporary cosmological simulations predict, which are the orange and the kind of pinkish mauve curves here. So for the same stellar mass range, their mass loading factors, in order to make dwarfs that are realistic in other senses, tend to be around 20 to 100. So how efficiently does star formation drive winds in low-mass galaxies? Well, star formation drives moderately efficient winds in low-mass galaxies, mass loading factor of around 1. This is in good agreement with direct observations of individual dwarfs and significantly lower than some predictions from cosmological simulations. So I said I was also going to be talking about distribution of star formation. So just to reset for a second, we're going to go back to the summary slide and ask, does the spatial distribution of star formation change with galaxy mass scale? And this is work that I'm going to be highlighting this individual project was led by a graduate student at Princeton, Abby Mintz. So dwarfs are important probes of the star formation cycle. That's kind of what I've been saying for the last 10, 11 minutes. But to use them as probes, one needs to actually find these dwarfs first. Large and low redshift spectroscopic samples are very resource intensive. As I said, the main SAGA selection, or the main SAGA survey has a selection efficiency of less than 1%. Medium band or narrowband imaging provides a new way to efficiently identify star-forming dwarfs. And obviously I'm setting up to talk about a medium band survey. So this is the Marian survey. We've been observing for the past around 4 semesters. It's a two medium band filters designed to capture H-alpha and O3 emission at redshifts between 0.05 to 0.1. Here's just our blue filter and our red filter. So they kind of sit just between the HSC broadband filters. And this allows us to first immediately redshift star-forming dwarfs, so really any star-forming galaxies in this redshift range, and also directly image the H-alpha emission. So this strategy can identify all star-forming dwarfs in view without a prior targeting selection. The full survey will contain about 100,000 dwarfs over more than 600 square degrees, and will be mass complete down to stellar masses of around 10 to the 8 stellar masses, again for star-forming galaxies. Of course, we're going to miss quenched galaxies with this scheme. So just to give you an idea of the early science results, this is led by Abby. We found that dwarf starbursts are differentially more compact compared to their massive counterparts. So on the left here, the white contours show the stellar continuum, and the color map shows star formation. And you can see that in these two low-mass examples, the starburst is preferentially more compact compared to the stellar continuum as compared to these more high-mass starbursts. So this is a potential sign of large-scale dynamical instabilities driven by low-mass interactions. And I'll just signpost this as more science to come with survey completion. So, to two punchlines. First, star formation drives moderately efficient winds in low-mass galaxies, and this is much lower than what some simulations use to make realistic dwarfs in other aspects. And dwarf starbursts are more compact than massive starbursts, and this could imply large-scale instabilities at play. I think I'm out of time, so let me leave you with this. Dwarf galaxies are a unique and increasingly accessible probe of star formation physics on galactic scales. Thank you.
Thanks. So if I understood correctly, your measurement covers about 2 orders of magnitude in stellar mass. Is that right?
Yes.
Have you tried to break this down into different, thinner, finer mass beams?
Yeah, that's a great question. Actually, so the limiting factor is just the number of galaxies in the Saga survey. One thing that we are thinking about doing is applying the same kind of methodology to the Desi-Lozi sample, which is a much larger sample. The reason why we started with Saga is because essentially the Desi-Lozi selection is built off of the Saga selection. So in order to understand one, you need to understand, in order to understand the Desi-Lozi selection, you need to understand Saga. But I think that's a great question because we do expect there to be perhaps some mass dependence in this regime.
The way that you calculate mass loading with the metallicity, let me see, how can I ask this? Essentially, what assumption, how far out does the gas need to be moving to be mass loaded? Like if somebody does a down the barrel measurement, they're basically just capturing all gas that is outside of the disk, that is faster than the disk. Or explicitly, people can go to the halo boundary as Marasco did. But where do your numbers lie in that range?
Yeah, that's a great question. So we're assuming essentially that the gas stays out in the halo or in the CGM for at least a couple of gigayears. But we also looked at what happens if we assume that all of the gas essentially recycles on around 500 megayear timescales. And we don't see a large change in the effective mass loading factor. Like we don't reach 20 or 100. But that's a great question, and I think it underlines that there's a lot of work to be done, both in how we compare observations to observations, like down the barrel versus, I think, down the barrel versus these recycling models, and also in the simulations, and you kind of have the same problem that some people measure mass loading factor through a slab at like 1 kiloparsec. Some people make a cut on the Bernoulli velocity. Some people trace gas particles individually. So I think there's still a lot of work to be done in order to reach a field-wide consensus, even on how to do an apples-to-apples comparison.
And your mass loading is all gas, basically. So it captures effectively the cold phases as well, like the H1 and the CO and the molecules, right?
Yes, but that's also a good point because the direct observations are looking at specific phases, like looking at H alpha emission, for example. Yeah.
So when you compare to like Christy McQueen, that's just ionized gas.
Yes.
And so yours should be a factor of like a few higher.
Yeah. It depends on obviously, as you know, it depends on how the phases are separated. But I think that the real driving point is that observationally, we're kind of developing a consensus from 1 to a few, whereas there's still cosmological simulations that predict 100. So I think that it would be great to reach the apples to apples, but we're also kind of in the apples to elephants regime still.
Thanks. Super interesting results. I wonder if you have any thoughts on the really large mass loading factors that the simulations seem to be showing, much more so than you. Do you think that's because their mass outflow rates are that much larger, or are their star formation rates reacting stronger and the star formation rate is going down? So in the ratio you have a very large mass loading factor, even though m dot out might not be very different.
Yeah, that's a great question. I'm definitely not going to say this is exactly why the cosmological simulations have a different mass loading factor right here. We also looked at the evolution of the star forming sequence, and we actually found that, and this will be the second paper of this series, we actually found that compared to observations for this mass regime, even at this low redshift range, the cosmological simulations actually have a shallower relation with redshift. So that implies that it's more to do with the mass outload or the mass outflow rate. But I'm not going to say, that's not my firm official stance, let's say.
Thank you.
Yeah, I changed the focus quite a bit. Yep, okay. So yeah, I'll talk about something slightly different, about early formation of galactic disks, both in general and more specifically about the Milky Way. But it's not kind of a bait and switch situation, because I'll also talk about turbulence and star formation in these early galaxies and show that it's tightly related questions. Okay. Now, there's a paradigm shift in galaxy formation. Until recently, it was strongly believed that these galaxies form late, at around redshift 2, because galaxies at high redshift seen by HST and ground-based IFU instruments were very clumpy, irregular, nothing like nice disks that we see around us today. But this view is highly biased, so this is rest frame UV, so we see active star-forming environments, and now with JWST and ALMA we have access to rest frame optical and ISM kinematics at these high redshifts, and it became clear that in fact disks are very common in the early universe, so the galactic disk can form extremely early. Closer to home, in our own Milky Way, with the advent of astrometric and spectroscopic surveys like Gaia, it became possible to see and trace the evolution and formation of the galactic disk in the distribution of stars around us, like shown in this plot from the paper led by grad student at Harvard, Vedant Chandra. And here, these points show the distribution of orbits of stars as function of their pentallicity. And metal-rich stars that form relatively recently, they all pile up at this upper bound of the distribution, so they correspond to this disky configuration. They formed in this nice disk, like we see in the Milky Way today. But the thing that was discovered only recently in several papers independently is this presence of dynamically hot component at low metallicities, which is thought to reflect this early phase of galaxy evolution before the Milky Way had any disk present. And in the same data, we can see the transition from this mass in the early universe, this nice ordered disk, and it happens very rapidly. And for the Milky Way, it also happens unusually early. In simulations, in small molecule simulations like TNG50, only roughly 10% of Milky Way mass galaxies form disk as early as is derived for the Milky Way. And in fact, we can go in the simulation and find very close analogs to the Milky Way in this phase and in terms of the mass assembly history and the disk formation in the early universe. So the results that I'll show now is essentially us trying to understand what's going on here within the first few billions of years of evolution when galactic disks start forming. And to do this, we take this galaxy from TNG, we extract it from the full cosmological volume and simulate it with a different code at high resolution with more detailed ISM, star formation, and feedback physics. And it is shown in this top row of panels. And for the comparison at the bottom, this is the original simulation of the same galaxy from TNG. So this is just a list of key improvements of this new model. So it includes explicit cooling down to low temperatures, depending both on radiation field and metallicity, and radiation field is modeled on the fly. And also there's a very detailed model for star formation and feedback, which I'll maybe mention later. But here I just wanted to draw attention to incorporating all these changes results in qualitative differences in the structures that galaxy form. In particular, it can form all this, now that we allow cooling down to low temperatures, it forms a large amount of these small-scale structures that are completely missing in the original simulation because of these high densities. The thermodynamics of gas in a large volume cosmological simulation are usually replaced by something like effective equation of state, which corresponds to much higher density, much higher pressures and temperatures that prevent formation of these small structures. So the effect on the star formation history is qualitative with this new simulation, which I, by the way, call ART, or just after the code that I'm using for these simulations. So the star formation history becomes much more efficient early on, and so the star formation rates are more than an order of magnitude higher than in the original simulation, and later they catch up and converge at around redshift 3. And the star formation rate is significantly burstier because of this cold, turbulent gas that we can now form in these simulations. And you can see that there are two different regimes of this exponential ramping up of the star formation rate and then flattening. And this kink at around redshift 7, it corresponds to the formation of the nice thin disk at around this early time. And in fact, and the properties of this disk are very consistent with what we see in this metal polar distribution of stars in the Milky Way. So it suggests that this disk could form as early as within the first billions of years. And just to remind you, so this is not an average Milky Way-like galaxy. From in the TNG, it was selected as being one that forms disk early, and in TNG it meant redshift around 3. So here with this detailed modeling of star formation and feedback, the disk formation is pushed to even more extreme regime to redshift 7. So all this very efficient star formation, burstiness, early disk formation, it's all reminiscent of this ideas that we hear from the data by GWST and ALMA, and we can directly compare. This galaxy that we have here, shown in blue, is consistent with many of the galaxies that is observed both in GWST and ALMA. So here, this is in terms of the rotational support of the disk, or presence of kinematically cold disk as a function of time, and mass star formation rate relations. It means that some of these early galaxies, or early disk galaxies seen in GWST and ALMA, can be progenitors of galaxies that will end up being Milky Way-like galaxies at redshift 0. And I stress it's only some of them because some other galaxies, like in ALMA, are at this point they're very massive starbursts, which will likely be progenitors of the group centrals and centrals of clusters. Okay, now with simulations we can also see how the properties of the ISM and star formation in these very early galaxies, how it's different from what we used to at redshift 0. And so one of the features of the simulations that help us is that in these simulations we forward modeled this local star formation efficiency per free-fall time on scales of star forming regions, so we can make predictions about this quantity, which in local universe is measured to be of the order of percent in typical star forming regions. And in simulations can be anything, but the model predicts that at this early universe, the typical average values of the star formation efficiency are actually quite close to what is observed in local galaxies. It's also close to 1%, a bit higher early on before the disk is established, and then below the percent later, and lower values are because of this higher turbulence in the ISM. So in this model, the star formation efficiency is coupled to the turbulence in the ISM on small scales. And another result is that the star formation efficiency varies significantly, almost by order of magnitude. And this variation reflects in the burstiness of the star formation rate. So a significant fraction of the burstiness in the simulations comes from the fact that turbulent ISM changes on very short time scales comparable to the local crossing times. And these time scales, efficiency of star formation change, and as a result, the star formation rate also change. And finally, the last thing I want to mention, because also been discussed discussed earlier, is a molecular gas. So in these simulations, we also model, have non-equilibrium chemical network for molecular gas, and molecular gas model completely separately from the star-forming gas, so we can make predictions about that too. And here they are shown with the molecular gas shown with green line, and blue is the star-forming, blue line is the star-forming gas. So then disk forms, the two trace each other quite nicely, so like just like we observed in the local universe, but at before the disk forms, these two are decoupled, so there's substantially more star-forming gas than a molecular gas, and this is something that was argued in the literature before. And here I also wanted to show this result to seamlessly advertise another work by a graduate student, Ava Paulson from University of Chicago, who investigated this decoupling between star formation and molecular gas using more idealized setup. These are simulations of isolated dwarf galaxies with the same detailed star formation and feedback physics, but with systematically varying metallicities. And at low metallicities, the ISM becomes much smoother, so molecular gas forms less efficiently, and importantly, star formation feedback destroys molecular regions before they can become fully molecular. And as a result, the abundance of molecular gas drops substantially by orders of magnitude in these low metallicity environments. And none of the existing analytical models for molecular gas actually captures this behavior. So Ava went ahead and calibrated a new model for molecular gas using the simulations, which is shown here with these magenta lines, and comparison gray histograms are the simulations. So if you need a model for molecular gas for your cosmological simulations or analytical models or to interpret observations, so this is the reference that you can check out. And I'll leave my summary here and take questions. Thank you.
I was just wondering, when you compare the TNG50 simulation with your zooming simulation with ART, about the sizes of the disk, does it change?
The size doesn't change that much. I mean, it also depends on what exactly how you define it. But yeah, what mainly changes is how disky the distribution is.
So if I understand, you were saying that your Redshift 3 disk in the simulation is similar in a way to the low metallicity disk of the Milky Way. But don't you expect, I mean, from Redshift 3 to Redshift 0 to have some kind of evolution like disk heating or changing in the properties of your disk?
Yes, that's a great question. So one of the peculiarities about the Milky Way, as suggested by inclusion by simulation, but also quite evident from the data, is that it formed quite early, assembled most of its mass early, and then it stayed in relatively unperturbed environment with like mainly just evolving without significant mergers that can affect the disk substantially. And what I meant specifically by the disk being similar at low metallicities is that actually like their low metallicity regime are below 10% solar. So here this dashed line is the Milky Way, and this blue line is the disk in this simulation. So it's like a similar formation of the disk signature. And most of the stars forming later will form at high metallicity, so it's really hard to do something about this population of stars by subsequent star formation.
So the next speaker is Romanelli, talking about environmental dependence of GMC evolution and star formation in nearby galaxies.
What's going on here? You see anything? No. Non capisco.
Esci e riparti, dai. Okay. Esci dalla presentazione, devi farla ripartire.
un'impostazione.
Speriamo, scusa,
Ah, sì.
fare un attimo così per se lo legge.
Se no lo stacchiamo e lo riapriamo.
Ok, dovrebbe
Ok.
partire.
Thanks. Ok. Qual è la luce? Ok, grazie. Okay. Hello everybody. I'm Andrea Romanelli. I'm a PhD student at Heidelberg University, and I work with Melanie Chevans on, sorry, on the GMC evolution life cycle. And today I'm going to tell you about what is the environmental dependence of GMC life cycle. So the idea of this project stems from the observational fact that clouds properties are environmentally dependent, and not only we see like galaxy to galaxy variation, for example, when we look at velocity dispersion, but also if we look closely to the inner subgalactic environment, we see variation also on the virial parameter, or the line size with yeah, the line width size relation. And indeed, among the most prominent morphological feature are also spiral arms. So spiral arms are a way to, so spiral shocks are thought to gather together gas, compress it, and in this sense could potentially enhance star formation processes. And indeed what we see is like an enhancement of the star formation rate density, but also of the molecular gas. But this does not necessarily translate in an enhanced star formation efficiency. And so the question here is about how this picture connects to how much clouds lives and what happens like when they start to form stars, and how this process whether it can be enhanced or not by the morphological environment where they lie in. So indeed, I was previously mentioned at the beginning of this meeting, it is debated whether clouds can live for a different amount of times, whether they found themselves in interim regions or in spiral arms. And there are, in fact, these structural morphological differences brought to the idea that it could be that clouds can live for a very long time in the interim regions, even to beyond hundreds of mega years. So the major question that I'm trying to answer within this project is whether what is the role of spiral arms, and whether indeed clouds in interim regions are longer lived, and also if star formation efficiency measured over the entire lifetime of a cloud is enhanced in spiral arms. So but how do we measure lifetimes? So here you see an overlay of two different traces of molecular gas in H2 region. So our group developed a method, a statistical method to measure lifetimes, which is based on the comparison of two different traces tracing two consecutive phases of a star formation process. So if you look at this picture and you average over the entire galaxy disk, you see indeed that they are correlated, and this relation is very well known. But if you focus your attention on single gas peaks, for example, and you draw an aperture around each gas peak, and you measure the gas to stellar flux ratio again, you would see that this ratio departs from the galactic average, because you're encompassing more gas inside each aperture. If you then
focus your attention instead on stars peaks, or at least like on the tracer of star forming phase, you indeed also have like departure from the galactic average, but in this sense, like you measure like a lower gas-to-stellar flux ratio because you're devoid of gas inside each aperture. And if you repeat this process for different aperture sizes, you can draw like a sort of tuning fork pattern to which we can fit an analytical model. So this model only depends on 3 parameters that fully characterize the cloud life cycle, which are and here you can see a representation of different fits. So these parameters are the cloud lifetime, so how much time a cloud on average spent on without showing any sign of star forming activity. And then the feedback timescale that tells you about the overlap phase between these 2 consecutive processes, and also which spatial scale, which is linked, at which spatial scale it decorrelates from the galactic average, which is linked to the region separation length. So we applied this method to nearly 100 of galaxies, and we measured the life cycle for all of these. And in a series of works, the main result was that on average clouds live for 16 megayears, so let's say 10 to 30 megayears, and this is consistent with free-fall timescale. They then start to form stars, and very quickly stellar feedback kicks in and start to sweep away all the gas. So the fact that this phase is very short gives a hint of the importance also of pre-supernova feedback. And since this phase lasts very shortly, this leads to a very low star formation efficiency measured all over the cloud lifetime. And this is consistent also with simulations. So from these PDFs, you see that indeed there's still some galaxy-to-galaxy variation, and we are trying to understand whether this variation stems from difference in morphology. So to come back to the question at the beginning, I would like to see whether these variations are at place also in spiral galaxy. So the data I used are from the Fang survey, which is a multi-wavelength survey of galaxy, pretty nearby galaxy, mostly face-on in the star formation main sequence. And we have a wealth of data characterizing a multi-scale process of the baryon cycle. You can also have a look at Catherine Krekel talk this afternoon about this. So to trace molecular gas, I use ALMA-CO maps, and while as a star-forming tracer, I use ground-based observation, H-alpha emission. And you can see here also an overlay of the mask that we use the environmental mask that we use to disentangle the 2 different environments, spiral arms and interarm regions. And we ran an experiment in these two different regions, applying the uncertainty principle of star formation. So as you can see visually, there are indeed structural differences, and indeed the average interseparation, inter-region separation is higher for interarm regions. You can see here like cumulative distribution of the inter-region separation. While when it comes to the cloud lifetime, we do not see any statistical variation between spiral arms and interim regions, nor for the feedback timescale. And this leads, so here you can see also like the p-value that doesn't allow to at least disentangle between these two environments. And also this leads also to basically no difference, a statistical difference in the star formation efficiency. So the answer here seems to be that clouds live approximately the same amount of time in arms and interarms, and do not necessarily, do not necessarily trigger star formation, or at least they don't make it quicker. So if not this morphological feature, we are trying to see whether there are other environmental dependence on these parameters. In a previous work of our group, it was seen that, for example, in NGC 300, there is a mild dependence of the cloud lifetime on the galactocentric radius, which is, again, consistent with the dynamical timescale. And we see also this in an enlarged sample of galaxies. So here each point is like a radial bin. And also, like another interesting fact about NGC 300 was that the region separation length is sort of consistent with the gas D-scale height, meaning that and we're trying to test this, but clearly it's still a work in progress. But this would mean that the star formation, the recycle of clouds is really feedback driven, because the gas D-scale height sort of sets the maximum distance at which you can find different clouds. And so perspective on this would be to also put a last block on this timeline, which is by having like high resolution and high sensitivity observation of dense gas. These are not at all to scale timeline, just an artistic representation. So we did this also with other tracer also on embedded star formation, like 24 and 21 micron. It would be nice to have like observation also on the most dense gas. And with that, I will leave to the conclusion of this work, so the take-home message, let's say, of this talk should be that clouds in spiral arms live for the same amount of time as clouds in interim region, and the duration of the feedback phase is also statistically indistinguishable between the two environments. And thank you for the attention.
Thank you very much for the very nice talk. So I have one comment and one question.
Yeah.
The comment is the same as what I gave to Rob. So what the tuning fork is measuring is the duty cycle of star formation rather than the lifetime of molecular clouds. So after the overlap time scale, clouds could go back to the original phase and stay without star formation, and then form stars again. And I think tuning fork is actually measuring the not the lifetime scale, but the duty cycle of star formation. That's a comment. And then the question is, the Fang's sensitivity limit is not that deep, and it's down to 10 to the 5 solar mass molecular clouds or so. So the other half of the molecular gas in each galaxy is clouds below the detection limit. So I'm wondering if your result applies only to the very massive molecular clouds rather than the whole cloud population, or you think that your result applies to all cloud populations?
So yeah, you're right. But at least, yeah, you're right. Probably there's a problem on the sensitivity. Yeah, we cannot go too much deep, like to see also low mass clouds. but I would say that most of the mass in each galaxy is of the mass molecular gas in the galaxy is concentrated in high mass clouds. So probably yes, probably we are missing low mass clouds, but yeah, I would say so to identify the gas peaks, we go as deep as possible, and still there is some arbitrary, let's say, criteria that one has to apply to select which are eligible gas peaks, let's say. But I would say that we are pretty confident we are measuring correctly the timeline in this case. Yeah.
Hi, very interesting to see the lack of difference between the arm and interarm environments. I was wondering, so the spiral arm pattern is moving with like a different velocity than the rotation of the disks at different, depending where you are in the disk, and so I wondered if you took into account when you do this like spatial decorrelation analysis?
If I took into account
the pattern speed essentially of the spiral.
The pattern speed. No, I didn't in this case. But since we also see other like for example, I try to input as many like environmentally dependent parameters as possible, like as for example metallicity, for example. So we see indeed there's it's not like a flat value for all the galaxy, and indeed this gives rise to a difference in the measure of the reference timescale. But yes, I didn't take into account that. Yeah.
I'm wondering, do you see a difference at the leading edge and the trailing edge of the arm? Because we expect the shock would change the distribution of gas structures.
No, I didn't look into it. No, sorry, I don't have an answer for that.
C'è anche ok, quindi si attacca tutti insieme, ok.
And the last speaker of the morning is Zibetti, talking about the specially resolved integrated relation of stellar population properties with stellar mass in present-day galaxies.
Okay. So great. Thanks, first of all, to the organizer for giving me the opportunity to present this work, which is actually a work that has been ongoing for almost 10 years now, mainly in collaboration with Anna Gallazzi and more recently with two students of the University of Florence, Daniele Mattolini, who is also here, and Jacopo Pratesi. So as you can read, the topic of this talk is especially resolving integrated relation of stellar population properties with stellar mass in present-day galaxies. And basically, the foundation of this talk lay in the idea that stellar population can be used as almost ideal tracers of the status and the properties of the baryonic cycle inside galaxies. So for example, if we put ourselves in this framework in which we can represent galaxies as a self-regulating star-making machines, we can model the galaxy as in the model by Lilly et al. 2013, in which a galaxy essentially takes gas from the surrounding environment, from its halo, and transform part of it into star, and part of this gas is left over and returned to the circumstellar environment, and partly is recycled. So the products of this machine, that is the stellar population, actually keep track of the production conditions. So essentially they accumulate the archaeological information that stems from this machine into long-lived stars. So for example, the star formation history that we can reconstruct from spectra give us the time dependence of the production rate of these machines. The metallicity distribution give us the efficiency of gas recycling, and the relative metal abundances give us information about the timescales and the IMF of these processes. Okay, so actually, if we look at the relation of stellar population properties with the stellar mass, we have what is the basis of one of the most fundamental knowledge that we have of galaxies nowadays, that is basically the archaeological downsizing, in which we know that the larger the mass of a galaxy, the faster it was the production of star, and the more efficient was the recycling. And we can see this from this plot that go back more than, let's say, almost 20 years ago by Anna Gallazzi with high mass star galaxies that are basically fully evolved galaxies with no more stars to form and no more metals to produce, whereas at low mass we have a large variety of evolutionary stages in which galaxies can still form stars and metals with a transition at around 10 to the 10.3 solar masses. So essentially this paradigm tells us that mass is king. So mass is what decides whether we are laying in a still active phase or we are essentially passive and dead. But there are evidence mounting that it is not it's not only the total mass of a galaxy that decides about this condition, but it may be also density or structure of a galaxy which decides whether we are still an active machine or a passive machine. So I would say that one of the fundamental questions that we should try to answer nowadays is which is the scale of the baryon cycle. So whether we are in a predominantly global scenario in which we can see galaxies as essentially monolithic star-making machines like this one, or whether we are in a scenario in which the predominant mechanisms are local, so we can look at galaxies as if they were distributed star-making factories made of many standardized machines. And by the end of the talk, I will try to answer this question. So in order to try and answer this question, what we looked at is the scaling relation of the stellar population. So to compare local versus global relation and try, first of all, to gain spatial information. In order to do this, we relied in the works that we have done in almost 10 years now on the Khalifa integral field spectroscopic survey. We were using almost 400 galaxies from the final release that sum up to more than 650,000 pixels with a resolution of around 1 kiloparsec and extended out to more than 2 effective radii. And we analyzed all these pixels using a Bayesian method that is based on indices and broadband photometry compared with a comprehensive library of composite star formation histories models with variable star formation histories, chemical enrichment, and dust attenuation. So here you can see a scheme of how this works. I don't have time to go into the details, but from all these maps of spectral indices and photometry, essentially for each galaxy we are able to determine maps of the distribution of the stellar mass density, like here, median likelihood light-weighted metallicity, and median likelihood light-weighted age, like this one. So this is an example from a spiral galaxy where you can clearly see that the spiral arms are younger than the interspiral arms, and you have a larger age in the center. Here you have an example of the maps that we can obtain spanning and going through the Hubble sequence, going from elliptical galaxies to later and later type spirals. And you can clearly see that there is a very stark difference in the ages of the spheroids, may it be the ellipticals or the bulge spirals, and you can see a very marked difference in the age of the spiral arms with respect to the interarm space. So what can we do with all this information at hand? We started by plotting the distribution of individual regions in these diagrams of local age versus local surface mass density. And you can clearly see that this distribution is not uniform, but it's clearly bimodal. We have two peaks in the distribution, and actually we can identify two separate sequences, like a young sequence down here, in which basically we have that the age of the regions increase with an increase in surface mass density, and we have an older age with almost constant old age, irrespective of the surface mass density. Now, what is very remarkable is that if we split the galaxies according to their morphology, we see that these two sequences are basically the same, but they are differently populated. So early type galaxies, of course, tend to populate mostly the older age, and the late type spirals only populate the young sequence, whereas intermediate spirals with bulges and disks populate the two sequences in different proportions. And you can actually see the example here of an edge-on spirals in which you see the disk that populates the young sequence and the bulge that populates the old disk. But it's also interesting to see that the relation remained the same even if we spin galaxies by global stellar mass. What changes is the amount of galaxies that end up in one sequence or the other, but the sequences are actually universal. So the global parameters decide whether the way we populate the two regions, but the sequences are actually the same. If we turn out to now look at the metallicities, the results are even more remarkable, because essentially what we end up is a quasi-universal relation between mean stellar metallicity and local stellar mass surface density. And these are the relations that you can see here. And actually, these two relations that you see here are for young sequence regions and older regions separately. But the two relations are basically identical. So these relations don't know about whether we are still active or passive. What only matters to determine the stellar metallicity of a region is the local stellar surface mass density. And this is really remarkable. We only see that if we go to two masses below the transition mass, we see that the relation between metallicity and surface mass density starts having an offset that we can see here in this plot, in which we bin galaxies according to different masses. Here we have the massive galaxies with all the relation overlapping to each other, and when we go below 10 to the 10, we start seeing an offset. And this is the same thing, rendition it as a map. But also we see that, for example, for early type galaxies, we see that the metallicity surface mass density relation is slightly offset as a function of the central surface velocity dispersion of a galaxy, whereby essentially galaxies with a higher velocity dispersion lay on a relation that is higher with respect to the galaxy with lower velocity dispersion. So essentially what we are seeing here is that we have a very strong quasi-universal local relations that are partly modulated by global physics, and this happens especially at low masses. Okay, this is remarkable, but it's especially remarkable when we try to compare these local relationships with relationships that we observe on global scales. In fact, works, for example, by Peng et al. 2015, also replicated with another analysis by Trassler et al. 2020, show that globally, passive galaxies and star-forming galaxies have two very distinct mass metallicity relations, with passive galaxies having much higher metallicity with respect to star-forming galaxies having the same stellar mass. So how can we reconcile these universal relations on local scales with these very distinct relations on global scales? And the fact is that we have to take into account that the passive galaxies and active galaxies have a very different distribution in stellar surface mass density. So in particular, we can say that on average, the stellar mass surface density of passive galaxies is higher than that of star-forming galaxies. So in passive galaxies and in active galaxies, we sample the local mass-metallicity relation over a different range of surface mass density. So this implies that the mean metallicity of a passive galaxy is on average higher than the metallicity of a star-forming galaxy of equal mass. And this is only related to the fact that the surface mass density distribution in passive galaxies and in star-forming galaxies is substantially different. Okay, so this is to conclude that structural differences are at the origin of the different global mass-metallicity relations, and this is not just a global mechanism, such as, for example, strangulation or outflow that determine this difference, but it's actually something that is happening on the local scales and a change of structure. So this leads me to the last point of my talk, and this is basically how can we actually go from a local scaling relation to global ones. And that this exercise is not as trivial as it might sound, because, for example, if we now try to plot the distribution of regions in our Khalifa galaxies in the plane that is determined by local age versus global mass of the galaxy they belong to, or local metallicity versus global mass, and we compare the trends that we find with the same, with the analogous relation that Galazzi et al. 2005 find for global properties, we find that the agreement is more or less good qualitatively, but it's not as good quantitatively. And this basically raises a lot of warning about how we can turn local scaling relation. How do we weight, for example, the different regions inside a galaxy, whether we should do this by area, by luminosity, by mass. And also we can ask whether SDSS data are actually fully representative of galaxies, and if the physical inferences are fully consistent. And this work now has been taking a few years, and also the help of our student in Florence, to try and understand better. One of the basic problems that we have in the SDSS, for example, is the fact that Sloan captures the light of galaxies only inside a fiber, and typically the fiber only collects 30% of the light of a galaxy. So how can we be sure that this light is representative of a galaxy? Well, actually, this is not really the case. Using Khalifa, we were able to simulate how a galaxy would look like in a SDSS fiber at different redshift. And you can see all these different spectra represent the same galaxy at the different redshifts. And you see that if you observe at very low redshift, we see predominantly the bulge, so red spectrum, old populations. Whereas if we move to higher redshift, we capture more light, and we are able to see the star-forming disk. So thanks to this exercise, we are now able to correct the full SDSS dataset to full apertures and see, for example, how the galaxy move inside an index diagram like this one. So we are able to see whether galaxies are well represented in sense of age and star formation. And for example, Daniele Mattolini will present his poster on Wednesday, have been able to estimate how the scaling relation, the global scaling relation, change, taking into account the full effect of this information. So I'm skipping the last few slides just to come to my conclusion. So it's very important to stress that we were able to find well-defined stellar population scaling relation on local subgalactic scale. So this highlights the fundamental role of density and structure built up. So galaxy evolution is not only determined by global processes and mass growth. Of course, there are still many methodological and modeling issues in order to bring on the same scale local and global scaling relation, but we can at least try to make some tentative conclusion. So local scaling relations are probably the most fundamental ones, and this is based on a universality argument that is based on the fact that the relation I was showing you before are universal throughout the Albus sequence and throughout the range of stellar masses. So global relation probably derive from the average of local properties weighted by mass distribution. Local relations are modulated, however, by global properties, which basically set the boundary conditions. And so all in all, coming back to the early cartoon that I showed in my plot, galaxies can be seen mostly as star-making factories, not just machines, with many standardized star-making machines linked by a common environment. So thank you, and taking questions.
Hi. In the very beginning, you briefly mentioned downsizing. I was wondering how, or can you even reconcile downsizing with the hierarchical galaxy formation model?
Yeah, this is actually a matter of a stark debate. I mean, I see Alvio Renzini here, who was one of the protagonists of this debate in the early 2000s. And essentially, this boils down to the fact that baryonic physics is decoupled from the dark matter physics. So we have a lot of mechanisms, most chiefly the feedback processes that essentially stop the star formations once the dark matter assembly is still ongoing. So you can reconcile an early stop of the star formation history of the most massive galaxies, whereby they still keep on building their halo mass, but without forming new stars. So this is just to cut a very long story short. I mean, we have like 25 years of literature on this, but I would synthesize this in a very compact way like this.
So beautiful talk, Stefano. So you showed us the two separate correlation, local relation with the age and with the metallicity. I was wondering if there is any merit in analyzing this in 3D. So if there are like two planes in the stellar surface density, metallicity, age, three-dimensional space that could basically contain all galaxies at redshift 0.
This is an interesting exercise that we are probably going to try next. Of course, whenever you have a more dimensionality, things get more complicated. I think so far what we have analyzed is the 3D space with local surface mass density, global surface mass density, and either age or metallicity. And for example, this one here is one example. The right panels try to analyze. Basically, you can build a three-dimensional cube using the two panels, in which you have local age and then surface mass density and global stellar mass. Then you can basically disentangle the two effects. And this was shown, for example, here, in which you have the full 3D information. Here you have local stellar mass, global stellar mass, color-coded by metallicity. So you can see the effect of the... So adding age on the top of that means going to 4-dimension even, which is starting being a bit complicated, but I of course see the merit of going and trying to correlate also the metallicity, because of course the things should go together.
Okay, let's thank Stefan and all the speakers.
Just a couple of announcements. So it's confirmed with your badge, you can enter the museum, the cathedral and everything. I just want to say that I told somebody that the monuments, the museum, they close at 8. It's true, but the last entrance is at 7:30. Okay. Then now we go for lunch. You follow us. There should be someone that tells me exactly where to go. We will go through the museum. Please do not stop now to look at the stuff. Otherwise, we will never reach the lunch. You can do it later, whenever you want. And in fact, with the badge, you can go in and out from these monuments anytime you want. You don't have just one entrance. You can leave your stuff here, the doors will be closed, and there will always be somebody, so you can leave your bags. Last thing, if speakers, please come to try to test your presentation before the presentation, at the coffee or the lunch before your presentation. If you're not sure when you talk, check the program online or take a printed program at the secretary. Thanks. 2:20, we start again.